we saw that since our model has a very small max depth, it's not very great. It's not a very good model. It's not going to be able to capture the signal from our data set. But we don't have to use a max depth of 2. We can go ahead and increase the size of our tree. Let's go ahead and try to increase the size of our tree. Let's see the resulting, how the model looks like. So let's go ahead and increase the depth of 3. So we have a max depth of 3. How many bins will we have? How many bins will we have? How many terminal leaves, how many terminal nodes and leaves will we have in our model if we have a max depth of 3? We're going to have 2 to the 3rd power number of leaves, since we have a binary recursive pattern. So to change a max depth of 3, notice how our visualization of our tree grows. It's bigger. So we have depth 1, depth 2, and depth 3. If we count the number of bins, I assure you there should be 8. Alright, so let's see how well our model works. So notice now we have greater depth to our tree. We're going to do a better job, so we're better capturing these high values there. But of course, it could be better, it can be improved. So I can go ahead and go here and change the max depth to 4. And our tree gets even bigger, so there should be 16 nodes here. Here's a resulting model. We can keep on repeating this process. Something like 5. Now our tree is very hard to visualize. It's a little hard to see everything, but this is the fit of our model, so it looks like it's doing a better job. But I'm going to go ahead and comment this line out. As we increase the size of our tree, it's going to take a long time to visualize it. Let's say let's bump it up to a max depth of 10. Very large tree. Let's look at the resulting model. Do you think this is a good model? If so, why? And if not, why? Do you think this is a good model here? Very large max depth, large number of bins to capture the behavior of our data set. In some ways, it's capturing some of the general trends, some of these large values here. It's doing this overall behavior. But we understand that our data has noise to it. There's always going to be noise in our data. Ideally, that noise is going to be very small, but there's always going to be noise. At this point here, we are allowing our model to be a little too adaptive. It's going to adapt too much to the training data. And if we allow our model to be too adaptive, guess what? It's going to start not only modeling the signal, capturing the signal, but it's going to start adapting to the noise in our data set. And we can see that in these points here. Look at this value there. Look at this value there. these sharp peaks. It's trying to adapt too much, trying to fit too much to our to their data set. Our model is too adaptive. So in this situation, our model has been overfitted. It starts fitting the noise. It starts memorizing the training data. If we have our depth if we increase our depth of the tree to be very large, such that each bin has only one training point, then our model isn't learning anything at this point. Our model is memorizing our data set. And we understand that if we memorize something, we're not really learning anything. We want to learn. We don't want to memorize. So increasing the max depth a little too much is a problem. But if we have a very small max depth, let's say a max depth of 2, then our model is underfitted. It's not very adaptive. So there has to be some intermediate value that's best to use. And as we saw here in this, what we've been playing around with, we're modifying max depth manually. We're modifying it manually, and we're observing which one's a better fit. But that's not very great. It's very hard to look at a graph and say which one is a better fit. Yes, the extreme of max depth of 2 and extreme of max depth of 10 is very clear. Those are bad fits. But what if, 4 and 5, or 5 and 6, or something like that? It's very hard to compare between 5 and 6 of max depth. So we need a better way, a more systematic way, to figure out what is a good max depth for our model. Now, this best max depth value will vary with different training data. will vary with the problem, with different problems you're working with. So just because we decide or we figured out that max depth of, let's say, 5 works best for our data, that doesn't mean that we should always use max depth of 5 for a different problem. We have to figure out, for this problem, what's a good max depth to use. So let's go ahead and start trying to figure this out. What we're going to have here, just run this here, is we're going to investigate max depth values from 1 to 19. And we have a for loop, right? So we don't have to do this manually. We have a for loop here that's going to calculate the mean squared error for different max depth values. Let's plot. And we see here is that as our max depth increases, the mean squared error of the training set decreases. So yes, even though having a larger max depth and general increase in max depth will lead to a lower training error, we cannot use that as a guide to figure out what's the best max depth value to use. A good max depth value in which the model doesn't start learning the noise from our data set. So using the training error isn't sufficient. So we got to go ahead and do something else. How do we go about trying to figure out if our model is generalizing to new data? Remember, if we have a model that does a pretty good job on the training data set, so what? We want to use our model to make predictions which we don't know the answer to. So we want to see how well the model will work with data it has not seen from, data it has not learned from. So one thing we can do is we can do a train test split. We can take our data set. We can go ahead and take our data set and partition it. Part of it is going to go to a training set, and part of it will go to a testing set. Now, this split is customary to be anywhere from 10 to 30%. Oftentimes we'll use 20, in this case we'll use 10. So this train test split, we can go ahead and write the function for it, but why do that? Scikit-learn already provides us a nice train test split. Nice function to perform train test split. We're going to shuffle the data, but we don't have to do that. In train test split, it will automatically shuffle the data for you. So the syntax is, we pass our data set, our x and y, we specify the test size. We can also specify the random state. And this will always use the same random seed when we do the train test split. So it's a nice way we can have reproducibility in our experimentation. So I'm going to set the random state equal to 0 here. Let's perform the train test split. So we said, okay, the training set should be 90% and our test set should be 10%. That's controlled by this keyword argument test size. We go and look at the resulting shapes of our training and our test set. We see that indeed the test is 10% of our original data set. I also encourage you to look at the documentation of train test split so you can understand the syntax. So we can pull out the documentation, and once again, this function is well documented. Okay, so let's go ahead and do a very same procedure as we did before in this block of code here. We're going to investigate for different ranges of max depth, different values of max depth. And the procedure is, we're going to train the model on the training set, but we're going to evaluate how well the model performed on the test set. And this is going to be different because now the model only gets trained on the training set. It's not going to be trained on the test set. It's a holdout set. So it's sort of like if I give you an exam. Let's say I'm a teacher and I give you a set of examples. With those set of examples, I give you the answers. So you understand the pattern, you learn the pattern, and I'm going to evaluate how well you learned the concepts. But I want to make sure you didn't memorize those examples. Didn't memorize the examples with what the answer is. So my test set, my tests that I give you, have examples that are different. Have examples that are different than what you saw. So hopefully, if you really learn the concepts, you're going to perform really well. If you had memorized the examples I gave you and didn't learn the concept I was trying to illustrate to you, then you would perform pretty poorly. Similar concept that's going on here. Train on the training set, the test set we're going to use to evaluate. So we're going to use, say, hey, with that trained model, go ahead and make predictions on this test set. We'll see what the model predicts, those predicted values. We'll go ahead and compare it with the true values. We have the true values with our test set and calculate some error metric that's going to describe how well the model performed. This is great because this will give us an idea of how well the model will perform if we give it observations it has not learned from. Remember, the test set are data points the model has not seen, has not learned from. It's going to create our for loop, investigate for different max steps. So we train the model in the training set, and we calculate the error on the test set. I'm going to plot the results. I'm going to plot them with our previous training set. So we see here that same behavior. As we increase the max depth, the training error is going to decrease. We understand that we cannot use that as a guide to figure out what's a good max depth value to use. But if you look at our testing error, we see that there's a minimum value, looks like around 7 that occurred here, around 7. So it starts to drop, our test error starts to drop, and after a while, around 7, it starts to increase. So in the space before max depth value 6, our model was underfitted. But as we increase the max depth, we reach this minimum value, and then as we increase the max depth, our model becomes overfitted. So now by using the testing error, we can figure out what's a good max depth value to use. And what I want to illustrate here is just we can look at the different max depth values, and it corresponds to how many bins, how many terminal nodes, leaves the model has. So it makes sense. As a model becomes very great, very deep, there's a lot of model parameters, a lot of ways the model can adapt to the data. But if we give it too much power to adapt to the data, guess what? It's going to start to memorize our data. It starts to capture the noise as opposed to signal. We don't want that.